Hello, everyone, and welcome back. Mr. High here, and we're continuing on with Chapter 6, Section 6.1.1. And remember in the last video, we talked about what E is, Euler's number. And it's a huge number. It's going to help us a lot, and it might help you a lot in your field because it's such a popular number in mathematics. Now, let's recall that and something else. So the big idea is we're learning how to differentiate the last two types of functions, which are exponential functions, such as y equals a to the x, and we want to learn how to differentiate log functions such as y equals log x. Okay. And we're going to get there, but in order to do that, we learned some background information where we learned what Euler's number is, E, which is Euler's number. Remember, it's pronounced Euler, not Euler. And that was equivalent to the limit as n approaches infinity of 1 plus 1 over n to the infinity. The idea that it comes naturally out of when you compound continuously. Okay? And why it's so applicable is remember that we compounded at 100% annual rate. So we're talking about it came out of when something grows or decays in a rate that's proportional to itself. Right? 100% means if you reinvest in your full amount, you get back your full amount proportional to whatever body it is. Now, that, however, is approximately just equal to a number, which is 2.71828, and it keeps going. Right? And this is an irrational number, just like pi, right? Where it keeps going on forever. But that's the big idea. So just remember, big idea here is that just know that E is just a constant. All right. It's a very magical number that has a lot of applications I'm sure you'll learn about if you continue in any STEM field. But for now, not for now, I guess you should know that, but the big thing is remember that E is just a constant. It's just a number, which is roughly 2.71828. Okay? Now, that's going to help us as we explore how to differentiate exponentials. So, what is the derivative of, say, e to the x? Let's start with that problem. Now, we don't know what that is, so let's use the formal definition of a derivative again, where we'd say the limit as h approaches 0 of e to the x plus h minus e to the x over h. Because remember, it's been so long since we've had math in this quarter system that the formal definition of a derivative, because remember, derivative is just how something is changing at a particular moment in time, an instantaneous rate of change. Is if you want to find how something is changing in a particular moment, okay, you want to find the slope at one point, well, we can't just find the slope at a point, but what we do know how to do is find the slope at 2 points, and then the slope at those 2 points, where 1 point is, say, h away, is you just calculate the slope between those 2 points, but then you want that h away to get closer and closer to 0. Minimize the distance between those 2 points, so when you find the slope between those 2 points, you can ideally say, or we're going to say that with limits, that the slope between those two infinitesimally small distance between those 2 points is equivalent to the slope at 1 point. And that's where that comes from again. Okay? Now, how do we go about this? Now, we can go about it algebraically, which is what we'll do here, where we can break this up, because it's exponents, as e to the x, e to the h, minus e to the x over h. And then I can factor out an e to the x and be left with e to the h minus 1 over h. Now, we can't plug that in. We can't evaluate this limit because we can't plug in 0. So if we instead do a number very close to 0 and see what that gives us, maybe it'll give us an idea of what this is. Now I'm doing 0.00001, 4 zeros and a 1. I'd argue that's pretty close to 0. Hope you don't disagree with me on that one. Now if I put this in a calculator, I technically wrote this wrong, and that would, in the math community, would upset some people, is I can't put in those numbers because I didn't technically evaluate the limit yet. When you plug in that number, that's you evaluating the limit, where you don't need to write that limit anymore. So it would look, this is the more accurate way of writing it. That is true. What I wrote previously is not a true statement. Well, not equivalent to what I'm trying to say. So what's this guy give us? Now, I'm only going to evaluate the numeric part of this. Okay. So if I do e to then, remember, e is on a calculator. It's right above the ln button, right here in blue. So if I do e to the point 1, 2, 3, 4, 1, and then I take away 1, oh, not up there though, minus 1, I get a really small number. I actually get 0.00001. And I divide by 0.41. Notice I get a number that's approximately 1. It should actually be 1. So what this gives me is e to the x times 1. In which e to the x times 1 is e to the x. In which you might, if you understood what just happened, you're like, wait, what? The derivative of e to the x is equal to e to the x? According to our algebra, it is. Now, you might be thinking, before we get into that, how did all of this become 1? Well, remember, and this is a good review of what e is, if I graph e to the x, e is just equivalent to 2.71828 to the x, which is just an exponential. So it's going to look something like this, where at 0, it's at 1, because anything to the 0 power is 1. Well, e to the point 0.00001, something very close to it, well, you're not quite at 1, because if you were at 1, that would go to 0. You're very close to 1. How far away you are from 1 is actually the same as the denominator, in which that's why it becomes 1. So that's fascinating. So the derivative of e to the x is e to the x. Now, what are the implications of that? And I don't know if implication is the right word, but what's that mean? To give you a better understanding is if I graph e to the x, and it would look something like at 0, it's at 1. At 1, it'd be at 2.718 roughly. So there's e to the x. Since the derivative of e to the x is equal to ex, that means that the slope at any particular moment is equivalent to its output at that value. So at 1, or at 0, so if I do e to the 0, well, e to the 0 is 1. What that also implies, though, is that means that the slope at x equals 0, or the derivative at 0, d dx, of e to the x at x equals 0, is also equal to 1. Right? So what that is saying is the fact that the derivative of e to the x equals e to the x means that the y value is equivalent to its rate of change at that moment. And it's quite interesting, honestly. That tells you a lot about e to the x. And that's the idea, again, is e comes from something growing proportional to itself. Right? So even at 1, if you did at 1, you're at 1 comma e, if you plug in 1, but that means that the slope at 1 is e. Right? That implies that the slope at x equals 1 is e. Okay? Now, that's great and all. And that's going to help us a lot. So if I start on a new page here, so what we know is that we just found out that the derivative of e to the x is equal to e to the x. Now remember that e to the x, that's, to give you some, make sure you're still with me, that's like 2.71828 to the x is approximately 2. The derivative of this is equivalent to 2.71828 to the x. Right? But that doesn't help us with all exponentials. Right? What about, say, y equals 2 to the x? Or y equals 3 to the x? How are we going to learn how to take the derivative of all exponentials? So let's look at 2 to the x and compare that to the derivative of 2 to the x. Let's see what's happening. Okay? If I make a graph of this, and I'll do 2 to the x in pencil, and I'll do the derivative of 2 to the x in red for some color. So we know that 2 to the x, and then we're going to look at, now how do you put in the derivative of 2 to the x? Remember that we can't put in this. So what we're going to have to put in, again, is we're going to have to put in when the value is very, very close to 0. So we're going to do 0.00001 of its formal definition. And I'm going to use the part of the definition where I already factored it out. Well, no, I won't do it. We'll do x plus 0.00001 minus 2 to the x over 0.00001. All right. Well, darn it, I did it again. I did the mistake that mathematicians, it's actually incorrect. So if I use the formal definition, the idea of what I'm going to put in a calculator is I'm going to plug 0.0001 in. So in a calculator, I'm going to put in for this function, I'm going to put in 2 to the x plus 0.00001 minus 2 to the x over 0.00001. Okay, and you'll see that here. So let's put in 2 to the x plus 0.12341 minus 2 to the x divided by 0.12341. And if I graph this, hold on a second, my dog is chewing on something. I'll leave it. Okay. 3 is 20. Well, if we graph it, notice that that first graph is 2 to the x. So 2 to the x in pencil is at 1. Well, let's see, at 0, I look at a table, at 0 it's at 1. And that's 2 to the x. And then the derivative of 2 to the x was at 0.693. So that's roughly here at 0.693. And you can see that it's growing at a slower rate. So you can say that the graph of e dx of 2 to the x is less steep, or is less than 2 to the x. Okay. Now, recall before I look at, say, 3 to the x, remember that if I did e to the x, and the derivative of e to the x, which was in fact e to the x, what we know is that they grow at a proportional rate. d dx of e dx is equal to ex, meaning that it grows at the same rate. Well, I don't want to use rate. Oh, we'll just use same for now, and I'll put it in quotations. Well, the derivative of 2x grows at a less steep rate, grows at a slower rate, right, than its values of its function. Now let's do y equals 3 to the x, and then also graph the derivative of 3 to the x. And I'll do this one in green and explore what's happening. And what we might even say while we're on 2 to the x is the fact that it's at 0.693, what we can even say is that since this grows at its same rate, you might say like 1 times e to the x is the derivative of e to the x. Well, this one being that it's 0.693 in relation to its original function 2 to the x, we might say that d dx to the x is equal to, you might say 0.693 times 2 to the x. Okay. Now, what if we look at 3 to the x? And the reason I got this, because I might be thinking to myself, you might not understand what I'm saying, is I'm talking about how it's growing in proportion to x. It's not growing at its full, at the same rate of 100% of its value. It's growing at 69% of its value, a little bit slower, less steep. What about 3 to the x? If I graph this, sorry, shouldn't use green for the graph. I'm going to use green for the derivative. We know that 3 to the x will look something like this. Okay. And now if I go in my graph and I change that to 3 to the x, and I change all these numbers to just 3 here, and I graph it, well, there's 3 to the x going through 1. Well, 3 to the x, the derivative of 3 to the x, sorry, I keep saying that, is actually steeper. And how much steeper is it? If I go to my table, we're at 0, it's at 1.0986. So it's at 1.099. I'll just put, for example, 1.099, where it's growing at a steeper rate. So we might say here that d dx of 3dx is greater than 3x, and it's more steep, or it's growing faster, you might even say. And how much faster is it growing? Well, it's growing 1.099, or 9% more than it is. So you might say the derivative of 3 to the x is equal to 1.099 times 3 to the x, and how it's growing. So what I'm going to leave you with is, when we're talking about derivatives of exponents, we want to be able to find the derivative of any number. The goal is we want to be able to have a rule or a function for a derivative of a to the x, where a is any number. But what we can see here is that when it's e to the x, we get 1. When it's 2 to the x, we get 0.693. When it's 3, we got 1.099. And now something to keep in mind too is, remember that e is roughly 2.71828. Well, that's greater than 2 and less than 3. And looking at the derivatives, 0.693 is less than 1, which is less than 1.099. So maybe there's a way, but what we see here is that there is some sort of constant in front here before we can just say times that same exponential. E to the x, if that a value is e, it's just 1. But if it's less than, it's going to be a constant less than. If it's greater, it's going to be a number greater than. How do we figure out what that is? And that's what we're going to explore in the next lesson. Okay? Hope that makes a little bit of sense. If you have any questions, please make sure you ask. All right, bye-bye.